Hi, my name is James McKone. I'm an assistant professor in the Chemical and Petroleum Engineering Department at the University of Pittsburgh. And I've been asked today to put together a little video that talks about some of the things that my research group does. Our research group is called the Pitt Redox Lab. We are an experimental applied electrochemistry group. Now, many of you may not be super familiar with electrochemistry. It's often not taught at the undergraduate level. The easiest way that I like to explain it is that we use electricity to both measure and manipulate chemical reactions. Our group also incorporates significant components of catalysis, chemical reaction engineering, and materials chemistry. Work in my group is heavily focused on advancing sustainability in the energy and chemical production sectors. Our mission is to invent technologies that will allow us to minimize and eventually completely eliminate the use of fossil resources in our energy and chemical economies. And we advance this goal by working specifically on technologies that incorporate electrochemistry, redox chemistry that can be controlled using electrochemical processes and tools. The type of research that we do is sometimes described as application-inspired or use-inspired basic research. This is a slightly more technical way of saying that we combined pure science and engineering research. Now, the way that we do this is by focusing all of our research projects first and foremost on some target technology. This might be a technology that already exists and just doesn't work as well as one would like it to. Or it might be technologies that simply don't exist at all, and we're conceptualizing them from the ground up. So we start from the position of trying to advance technology, but then what we do is we analyze these existing or not yet existing technologies with respect to where are their pain points, which is to say, where are the unknowns or the challenges in the underlying chemistry and physics that govern the behavior of these types of technologies, that if we solve the problems associated with those underlying chemistry or physics, we would immediately advance the practical viability of that underlying technology. And so we design experiments that look kind of like a hybrid between what you'd see in a science lab and an engineering lab. We do hypothesis-driven work that's a little bit more scientific to try to solve these scientific challenges and understand physics and chemistry that go on in our electrochemical devices. And then once we've solved those problems, we have already then made a meaningful contribution to advancing the underlying technology. And so our lab also does undertake some design work to prototype small-scale devices that we can use to demonstrate to ourselves or to the broader research community that we have indeed improved that technology. So let me give you an example of the type of work that we do in my lab. One of our major projects is on the environmentally sustainable production of hydrogen. The way that we're doing this, or we're targeting this, is through a process called water electrolysis, which is a way of using electricity to extract hydrogen directly from water instead of using hydrocarbons as the basis of hydrogen production, as is currently done industrially. The challenge, the scientific challenge that we're trying to undertake here is that current generation water electrolyzers produce hydrogen that is way too expensive, and the reason is because the systems require the use of corrosion-resistant materials and precious metal catalysts, all of which significantly contribute to the cost. And the reason that this has to happen is because they all operate under acidic conditions where only a limited number of materials are stable. And so what we're doing is developing, in our lab, a new generation of catalysts that are designed to operate at nearly as efficiently as those that operate precious metals that operate in acid, but instead work under alkaline or basic conditions. And that allows us to transition from using very expensive materials like platinum and iridium to very low-cost materials like nickel and even iron. And so if we're successful, and in fact we work with lots of other people in the community that is all working toward this transition toward alkaline operating conditions for water electrolysis, success in that area would be a major breakthrough in our ability to generate this very important commodity chemical hydrogen in a more environmentally sustainable way. All of the research projects in my group incorporate some combination of electrochemistry, of engineering design, of scientific experimentation, and in many, many cases, materials synthesis. And so the skills that you gain as a member of my research group, whether you participate at the undergraduate level, at the master's level, at the doctoral level, or if you're coming in at the postdoc or staff level, give you a set of skills that are useful in a wide range of potential employment opportunities down the line. Examples of jobs that students in my lab have been and would be very competitive for include traditional chemical manufacturing jobs or emergent high-tech industries like electric vehicle manufacturing and battery manufacturing, to startup companies that are developing technologies to mitigate climate change or invent completely new ways of thinking about using chemicals and converting energy, and certainly a whole host of job opportunities in academics or in the government sector, both technical and analytical or what have you. So if any part of this sounds exciting to you, I encourage you to check out our website at mckonelab.pitt.edu or consider reaching out to me or any one of our lab members by email. Thanks very much for listening.